Okay, so in last class we discussed about analysis by IR spectroscopy, and in this section I have to add more points. So we discussed about the frequencies, different frequencies corresponding to different vibration. One is the skeletal vibration or fingerprint bands that will produce fingerprint bands. So the skeletal vibrations, that is with all the atoms vibrations we have to consider all the atoms inside the molecule as a whole, that kind of vibration. So it depends on the molecular structure of the atom, molecular structure. And second one is that the characteristic group vibrations, and which is dependent on individual groups present in the molecules. So only some portion of the molecule will be taking part in such kind of, and that will give you group frequencies or group bands in IR spectrum. So for different groups like white, C, O bonds, all those things, we have different frequency bands in IR spectrum. So if those groups are present in your molecule, then correspondingly we get particular bands in IR spectrum. So these are the different vibrations. When we consider the fundamental mode of vibration, these two are the different vibrations that is there in your molecule. So these two vibration, one is skeletal vibration and characteristic group vibrations are there in, that will provide you the IR. So corresponding to these two vibrations, we have different frequencies that you can observe. And in this frequency, all the frequencies will not be at the same position. When you are considering the IR spectra, we cannot get all the frequencies exactly at the same position in some times. Sometimes you will get all the frequencies corresponding to different vibrations in the same point or the same band origin. But in some cases, the frequency may shift from its original position to some other position. Okay, so this kind of this kind of vibrations, correspondingly, these vibrations will produce different frequencies or frequency bands in the uh, IR spectra, and that should be at some particular frequency bands or some particular frequency position in centimeter inverse. But in some cases, there can be some shift. It is in some cases. So there can be some shift that can be possible. For example, let's say if you are having some bond, for example, let's say C or bond. This is not the actual value, but let's say this is at some 2350 centimeter inverse. But in some cases, we will not get this frequency at this position corresponding to this year. It may be shifted to some 200,500 or something like that. So the shift can be possible in the IR spectra in some scenario. So in what kind of process which will lead to this kind of frequency shift in IR spectra, that we will be discussing this section. Okay, so first possibility. So first we are considering the frequency shift frequency shift is um, we can say may occur. So shift may occur. Okay. So this may occur because of first let's consider the resonance. The resonance. So reason for the shift is resonance. So, for example, if you are considering that carbonyl group, okay, in that ketone, and the C double bond or C in some other group. So these frequencies are almost very close to each other, and so in some cases, these frequencies can change energies between them, and that will lead to a change in their position, because when the change in energy happens, frequency also change, is going to change. So the spectra will move somewhat in a different position. Okay, so if you are considering that ketone group, so let's say this ketone, in this ketone we are considering this carbonyl group C double bond O. So this carbonyl group, I'm talking about this carbonyl group C double bond O. This carbonyl group in this ketone, so this entire molecule is ketone, okay? And this is carbonyl group. Carbonyl group. So this carbonyl group frequency in normal case it is at 1750. And if you consider any other CC double bond like this, okay? So in this case, this double bond, if you consider, this is having a frequency of 1650. So this is somewhat some 65 centimeter inverse is the difference between these two frequencies in your spectra. So sometimes these two frequency will share energy, which is called as resonance. Some resonance can be possible between these two bands, and the energy can be changed from one band to the other. And after resonance, the bands will be at 1675 and 1600 centimeter inverse. So this 1650 will go to 1600, and this 1750. So this kind of shift in spectra, that can be possible. So what we are going to say is that this is centimeter in centimeter inverse. We are talking about the spectra, IR spectra. So in IR spectra, we have the position uh, for this carbonyl group at 1750. We are considering 50, okay, and the C double bond C somewhere 1650. This is at 1750. And if you are considering these two bands, you will be having peak. You have to get peak at 1715. Similarly, you have to get the peak at 1600 like that. So maybe intensity. Oh, okay, this intensity is very double bond C. So this will be small. Now, if you are considering the resonance process, and after resonance, the frequencies will shift its position, frequency band in terms of centimeter, and will shift its position. So, this is at 1750, this is at 1650. So, this 1750 will change 1675. So, somewhere around here we can say 1675. And somewhere here 1600. Okay, let's say this is 1000. It's not the exact scaling. So we will be having a shift of these frequencies after that resonance. That resonance means some of the energy from this will be transferred to this peak. Okay, that is the resonance process. And after resonance, we will be having some this frequency at standard at 1675, for example. And this one will go to 1600 with some more density because energy transfer of load. We have more intensity corresponding. So after resonance, the intensity of this 1650 will be comparable with that of 1675, which means that this is the C double bond O group. This is the C double bond C group. Okay. So before that resonance process, we have the intensity which is very different between these two bands. Consider 1750 intensity is very large as compared to the C double one C. So after resonance, but after resonance, if you consider the intensity of this C double bond C is also comparable with that of the C double bond of frequency, that peak intensity. Okay, so that is the resonance process. After resonance, there is a possibility that the frequency may shift, the frequency of the bands may be shifted at some different positions. Now, the second one, that is second for frequency shift, is that occurs from the change in physical state. Yes, change in physical state. So change in physical state means that if you're working with a sample in gas form, in liquid form, in solid form, so that also depends on the frequency of your band or your spectral peak position. Normally, that will be having uh, a tendency of frequency in such a way that in general we can say general the frequency which is associated with the gas will be much higher than that of frequency associated with the liquid. This is almost equal to the frequency associated with any solvents if you are using, and then which is much higher than that of solid. The solid will be having frequency which is less. That is obvious because the vibrations that will be less in the solid state. And so similarly, if you are considering the polar molecules, okay, polar molecules means that the molecules with charges on both. If you are considering, for example, HCl, that is an example for these polar molecules, and the hydrogen is positively charged chlorine. So such molecules are called. And for polar molecules, the shift will be uh, comparably much higher. Okay? Shift is higher compared to normal mode. So comparing with normal molecules, polar molecules will be having larger shift with the physical state change. Okay? We are talking about physical state change. So for example, if you consider that HCl, okay, so if you consider HCl molecule, so HCl molecule is a polar molecule, and that will produce a change in frequency when it is going from the gaseous to liquid state. Okay. So if you consider vapor, so if you consider that change from vapor to liquid for this HCl, there will be a shift of, this will produce a shift of 100 centimeter. Okay, so if the HCl move from vapor to liquid, then there is a shift of 100 centimeter inverse. And if this liquid is going to become a solidification, or this process is solidification, and this is, if it is going to become solid, okay, then it is going to have a shift of 20 centimeter. But if you consider the carbon dioxide, for example, another example, a non-polar molecule. So in the case of it's a non-polar molecule, and in this case, if you are considering vapor to liquid transition, and in that case, the shift is negligible. There is negligible shift. But when it is going from liquid to solid, that is solidification of this carbon dioxide, then in that case, it is having a shift in frequency of 60 centimeters. So what that actually means is that if you are having your spectra, for example, in this HCl case, you are having your spectra at this position initially, okay, corresponding to this HCl bond, which is having a spectra at this position. For example, I'm just saying an example that this band, for example, it is at this is just an example. So this is at some x position, and if you are converting, this is in the case of vapor, this vapor state. So if you are converting that into liquid form, then you will get a spectra is having which is having a shift of 100 centimeter inverse. So it can be plus or minus. Okay, I don't know where it will go exactly, but let's consider it this number here. So this is just for an understanding purpose. So this is not the exact. So it can be x minus 100, can go that shift. So it will go from initial band to some 100 centimeter inverse, less than that of the first one, or it may be greater than that of the first one. So a 100 centimeter shift is possible when you're having this kind of thing. So normally, if you're considering this, this is the gas state which is having higher frequency. Okay, so solid state will be having low. So liquid state is less than that of gas, right? So it should be less than that of initial frequency. So I think minus 100. because when it is converted into liquid, it should be less than that. Yes. And also remember that frequency, okay, when we are talking about frequency, okay, if the frequency is larger, lambda is smaller. Okay, so when the frequency is larger, lambda is smaller, and we are talking frequency in terms of wave number, and wave number is nothing but 1 by lambda. Okay, so when your frequency is higher, your 1 by lambda, which will be larger. So because lambda is smaller here, frequency is larger. And when frequency is larger, 1 by lambda is larger, which means that frequency will be proportional to whatever your band position in centimeter is. Okay, so if it is having higher frequency of vibration, you will be getting a higher number in your band, higher spectrum in centimeter. So that's why I'm talking about every time when I talk about frequencies larger, I have to take larger wave number also. Because when frequency is larger, wave number will be also large. Which means that otherwise you can take it like this also. If you are having a wave like this with some frequency, or if you are having a wave like this, so the number of waves per centimeter per or per meter, if you are considering in these two cases, number of waves will be larger in this case with high frequency as compared to this case. So when frequency is higher, the number of waves per unit length, that is in centimeter or in meter, we are considering in centimeter in this particular case. So that is proportional to the frequency. When frequency is higher, the number of waves within centimeter. For example, if you consider this is a centimeter, and you calculate what is the number of waves which are coming within this centimeter, 1 centimeter, for this particular frequency. So if frequency is larger, number of waves per unit length will be larger, which means that the wave number will be larger in that particular case. So frequency is directly proportional to the wave. So the number of waves will be increased when frequency is larger. So when we are talking about 1000 centimeter inverse, which means that 1000 per centimeter. So 1000 waves will be the in that particular uh, that particular wave which is coming out of the sample. So 1000 wave per centimeter. That is the meaning of that spectral x-axis. So 1000 centimeter inverse means 1000 waves per centimeter. If you are considering 1 centimeter, there will be 1000 waves. So okay, that's all about the basics related to this. So basically, frequency is directly proportional to the wave number. So if you are having higher frequency for gas, then you will be having higher wave number for gas state, and similarly for the case of solid, it will be less. And so if you are having a vapor at X position, that is for HCl molecule, it will be having 100 centimeters change or shift when it is going to liquid, and liquid is less than having a frequency which is less than that of gas. So we have X minus 100 when it is converted into. So this shift is possible when you are having a change in state. Okay? So that is the second possible reason for the frequency shift in the IR spectrum. And the third possibility, this is not actually the change in frequency for a particular band, but we can say a frequency shift. So we are not going to take this under that title, but we can say a frequency shift. Frequency shift is possible uh, with the change of atom in the group. Okay, this is also possible. So this is somewhat little different from the previous cases because we considered physical change and resonance. And in that case, we are considering same molecule, same group we are considering. But in this case, we are considering same group but different atoms, same kind of bonding but different atoms in that position. For example, if you consider CH and then we have CF, then CCl carbon for CCl carbon for CL4 or something. So CCl and then CBr. Okay. So in this order, if you are considering this in this order, so hydrogen is less mass than chlorine, than chlorine, than bron. So in this cases, the mass is getting increased while moving in this direction. Mass is getting increased while moving from hydrogen to bron. Okay, so in that case, you are having higher mass for the entire molecule. And if you consider the wave number equation, mu bar, which will be equal to 1 by 2 pi c root k by mu. This is the wave number equation. Okay, so if you are considering this particular equation, now we have this mu, which is coming the denominator. So when you are having larger mass, you will be having small uh, wave number. Okay, so which means that if you are having hydrogen, so I will just plot as an example. So this is not the exact spectrum. So this is your CH bond, for example. So this is your CH bond, and if let's say this is at X, and then if you are having CF, then it will be having somewhere here. I'm not talking about the intensity variation of those things. I'm just talking about the frequency. So this will be X minus some delta X, for example. Okay, so it will be less than that of CH bond because the fluorine is having more mass as compared to CH, H hydrogen. So the total molecular mass will get increased when you substitute that atom with hydrogen with C. Similarly, any other atom, if you are substituting, then the mass will get increased or decreased. According to that, the frequency will change. The frequency of vibration will change. Then the wave number also. So that is the effect of mass. Similarly, if in the same concept we have another important thing, if this is also will be affected by the bond strength. Okay, so increasing strength of the bond, increasing strength of bond increases frequency. You're having the bond is very rigid and which is having the strength of the bond is very high, then that will increase the frequency. Okay, so if you are having larger mass, then it will decrease the frequency and the wave number. And if you are having strong, very strong bonding between these atoms and increasing the strength of the bond, that will increase the frequency and the wave. So let's consider the different bonds CX. Then we have C double bond X. Then we have C triple bond X. So this in this direction, we are having very strong bond at this end. So the force constant is going to increase, or we can say the K value in this particular expression will get increased. So since the mu bar is directly proportional to this force constant, and because of that, the frequency will also get increased, or the wave number also will get increased. So in this case, how the spectra will look like? So the spectra will be like you are having initially your spectra at this position. This is at Cx. It will be moving somewhere here with the double bond X, and then in this case I have to write. So I will change this parameter Cy of X. So C double bond Y. So here it is C double bond Y. This is double bond Y. Here I'm having this X, and here I will be having X plus delta X as my wave number. Okay. So if you are having increased bond length, bond strength, we'll be having larger value of K, and we will be having higher frequency. And now one more point in here is that more polar the bond, more intense will be the spectrum. So we are not talking about the. So these 2 points you can take out from that main heading, but you can take. So this is more polar the bond, more intense will be more intense will be the spectrum. So if the bond is more polar, then the spectral intensity will be large. Okay? So for example, if you are considering C double bond O, the C double bond N, then C double bond C. Okay, so if you are considering this, then so the intensity, now we are talking about intensity, not about frequency. So the intensity will be decreasing in this order, because it is more polar with C double bond O, okay, as compared to C double bond C. So in this direction, polarity will get decreased. So in this direction, the C double bond O molecule will be more polar as compared to the polarity will get decreased in this direction. So the intensity also will get decreased. So this is, I'm talking about the intensity of the spectral line. Okay. Each of these C double bond O position will be different, C double bond N position will be different. But when you consider the intensity, frequency, and the spectral position will always will be different, because we have different atoms in these branches. So the frequency will be always different anyway, but the intensity also will be different in such a way that the more polar the molecule, more intense will be the spectrum. So in this case, C double bond O will be having more intensity as compared to C